In April 2024, the largest map of the universe ever made came back with an answer nobody wanted. The force driving the universe apart, 68% of everything that exists, is not behaving the way our model says it should. It is changing, and a force that changes points toward a different future than the one we calculated. We have known about dark energy for 25 years. We have never explained what it is. Not what it does, what it is. The honest answer has always been a name we gave to something we cannot explain in an equation that happens to fit the data. Now, the equation is starting to not fit. The 2024 data places dark energy past a specific boundary in the mathematics. A boundary where the calculations change character entirely. Past that boundary, the universe does not fade. It does not cool. The technical term for what happens past that boundary is the Big Rip. And the DESI telescope just measured us on the wrong side of it. To understand what that means, you have to start in with a man who invented this entire problem by accident and spent the rest of his life trying to undo it. He never managed to. In 1917, Albert Einstein had just finished general relativity. He ran his own universe through the new equations and found something wrong. Gravity pulls. His math said the universe should be collapsing inward on itself. But Einstein looked up at the sky, and the universe was just sitting there. Calm, static, not collapsing at all. So he did something he would regret for the rest of his life. He added a term to his equations that he had no physical justification for. A constant. He called it the cosmological constant, the Greek letter lambda, and he set its value precisely to counterbalance gravity and hold the universe still. He knew it was a patch. He called it his biggest blunder. Then, in 1929, Edwin Hubble measured the velocities of distant galaxies from the Mount Wilson Observatory in California. Every single one was moving away from us. The universe was not static. It was expanding. Einstein heard this, crossed lambda out of his equations, and moved on. The blunder was gone. For 69 years. In 1998, two teams measuring the brightness of exploding stars found that the expansion was not slowing down. It was speeding up. Something was pushing the universe apart. And that something behaved exactly like Einstein's cosmological constant, the term he had crossed out, the term he had called his biggest mistake. Saul Perlmutter, Brian Schmidt, Adam Rees, Nobel Prize 2011. The biggest blunder turned out to be right. If that sounds like a triumph, ask yourself what it actually means. The dominant force in the universe is something Einstein invented to make his equations work, then rejected, then died convinced was wrong. And it is real. How comfortable does that make you feel about the foundations of everything else? After 1998, physics needed a name for whatever was pushing the universe apart. They called it dark energy. And here is what that name actually means. We have no idea what it is. Dark energy is not a substance, not a particle, not a field we understand. It is a label, a placeholder that sits in an equation and makes the equation fit the data, with nothing behind it explaining why. 68% of everything that exists. Think about that number for a second. You are made of atoms. Those atoms, and every atom of ordinary matter in the observable universe, add up to 5% of the total content of reality. Dark matter, the invisible scaffolding around galaxies, is another 27%. And dark energy is 68%. The thing that constitutes the majority of the universe, the thing that controls whether it expands or contracts, whether it ends in ice or fire or something we have no name for, that thing is physically a label with a question mark. We called it dark energy and moved on, built a model around it, won Nobel Prizes with it. And for 25 years, almost nobody asked the question that is now burning through the field like a slow fire. What if the placeholder is wrong? Not wrong in its value, wrong in its nature. Not a constant, something that moves, something that evolves, something that has been doing something for 11 billion years that our model assumed it was not doing, something with a future that our model cannot predict. Does that strike you as a satisfying foundation for 68% of everything? The standard model of cosmology is called Lambda-CDM. Lambda for the cosmological constant, CDM for cold dark matter. Built in the late 1990s from supernova surveys, the first detailed maps of the oldest light in existence, and galaxy clustering data, and it works. It predicts the distribution of galaxies across the sky to fractions of a percent. It predicted the abundance of helium and deuterium produced in the first 3 minutes after the Big Bang. And when we measured those abundances, they matched. By almost any standard, Lambda-CDM is one of the most successful scientific models ever built. And yet, Lambda-CDM does not tell you what dark energy is, does not tell you what dark matter is, does not explain 95% of the universe's actual content. It describes their effects without describing their nature. Think of it this way. Imagine you have a complete map of a city, every road, every bridge, every highway, drawn with perfect accuracy. But every building on the map is labeled unknown structure. You could navigate the city perfectly. You would have no idea what was inside anything. Lambda-CDM is that map. Perfect navigation. No understanding of what the buildings are. For 25 years, physicists navigated with this map and largely did not worry about the buildings. The roads worked. The predictions matched. Why ask what is behind the label? Because in 2024, the roads started looking wrong too. And when the roads in a map with no buildings start looking wrong, what exactly do you trust? In 1989, Steven Weinberg at the University of Texas sat down and wrote out what quantum field theory actually predicts for the energy of empty space. This is not an exotic calculation. Quantum field theory, the framework that describes how particles interact, the most precisely tested framework in the history of science, predicts that the vacuum is not empty. It seethes with virtual particles constantly flickering in and out of existence, borrowing energy and returning it almost instantly. This is not a metaphor. In 1997, Steve Lamoureux at Los Alamos placed 2 uncharged metal plates very close together in a vacuum. They were pushed toward each other, by nothing, by the energy of empty space pressing in from outside. He measured the force. It was there, exactly as predicted. The vacuum has energy. Established fact, not philosophy. So Weinberg calculated how much, used the standard equations, got a precise number, then looked at what astronomers actually measure for the energy density of dark energy, the thing accelerating the universe, compared the 2 numbers. The theoretical prediction was 10 to the power of 120 times larger than the observation. Not 10 times larger, not a million. A 1 followed by 120 zeros. The worst failure of dimensional analysis ever recorded in any field of human inquiry. Weinberg published, called it the cosmological constant problem, noted it was the worst prediction in the history of physics, and sat back. That was 1989, 35 years ago. Right now, as you sit there, this is the foundation underneath everything we claim to understand about dark energy. Does that feel stable? To feel the scale of 10 to the power of 120, you need an image. So here is one. You are an engineer, asked to calculate how much weight a bridge can hold. You use the best structural equations available, equations verified thousands of times that have never failed on any bridge ever tested. Your calculation comes back. This bridge will hold 1 kilogram. Then you watch a freight train cross it. The train weighs 10 to the power of 120 kilograms. The bridge holds, every time, for 70 years. That is the situation quantum field theory is in. And here is where it stops being abstract and starts being personal. If the vacuum energy were actually as large as the equations predict, the universe would have expanded so violently in its first moments that no structure could ever have formed. No galaxies, no stars, no planets. The matter that eventually became your body would have been scattered into an expanding void before a single atom could have found another atom to bind with. You exist because this number is wrong by the largest margin ever recorded in science. Your existence is the evidence that the calculation failed, and nobody knows why it failed. The bridge holds, the train crosses, every time, and nobody, not in 1989, not in 2024, not now, has found the error in the engineering. So here is the question that sits underneath all of cosmology, underneath DESI, underneath everything we are about to go through. Are we dealing with an error in the calculation? Something nobody has found yet? Or are we dealing with something else entirely? Something that means the calculation is not just wrong, but asking the wrong question? There are 3 ways physicists have tried to live with 10 to the power of 120. Not solve it. Live with it. Because in 35 years, nobody has solved it. The first, quantum field theory is missing something. A deeper theory will eventually show that the real vacuum energy is small for reasons we cannot yet see. This is the optimistic view. It requires that the most successful framework in the history of physics is fundamentally incomplete at a scale nobody has found yet. The Large Hadron Collider ran for 15 years searching for that missing piece. It found the Higgs boson, confirming the standard model, and nothing else. The second, supersymmetry. Every particle has a partner with opposite quantum numbers, and the vacuum energies of particles and superpartners cancel almost exactly, leaving behind the small observed residue. Like 2 enormous debts that almost cancel each other, leaving a tiny balance. The cancellation has to be precise to 120 decimal places. The LHC searched for the superpartners at every energy scale the theory predicted they should appear. Found nothing. The third approach makes most physicists look uncomfortable when you bring it up. The cosmological constant has the value it has because if it were different, larger or smaller by almost any amount, we would not be here to measure it. It is a selection effect. We live in the rare universe where the number landed in the window that allows galaxies. This argument is logically correct. It is also deeply unsatisfying. Because it means the answer to why dark energy has the value it has is, because in the universes where it does not, nobody is asking. 3 approaches, 3 decades. Which one is right? In 1987, Steven Weinberg did something unusual with that third approach. Instead of treating it as philosophical resignation, he used it as a prediction. He reasoned, if the cosmological constant were much larger, the universe expands too fast. No galaxies form, no observers. If it were large and negative, the universe collapses before stars evolve. The window compatible with observers is narrow. He calculated where in that window the constant should sit, if selection is the explanation. Published the result. 11 years later, Perlmutter and Rees and Schmidt measured the cosmological constant. It landed inside Weinberg's predicted range. Either a remarkable vindication of the anthropic approach, or a coincidence. What it is not, and Weinberg himself was careful about this, is an explanation of what dark energy physically is. Here is why 2024 made this urgent. Weinberg's entire framework assumed lambda, a fixed, unchanging cosmological constant. The selection window, the predicted range, the whole structure, built on the assumption that dark energy does not evolve. DESI has now measured dark energy across 11 billion years of cosmic history, and the measurement says it is not fixed, which means the most complete theoretical framework for understanding why dark energy has the value it has, 30 years in the making, was built on an assumption that may be wrong. Not wrong in the details, wrong in the foundation. And the question now is not just what dark energy is. The question is whether anything we thought we understood about why it has the value it has was ever pointing at the right thing. Where do you start when the explanation for the unexplained turns out to need its own explanation? In 2013, construction began on an instrument fitted to the Mail telescope at Kitt Peak in the Sonoran Desert of Arizona. The Dark Energy Spectroscopic Instrument, DESI. The task: measure the positions and recession velocities of millions of galaxies spread across billions of light years, precisely enough to reconstruct the history of the universe's expansion at multiple points in time simultaneously. 5,000 robotic fiber optic positioners mounted on the telescope's focal plane, each one repositionable in under a minute. Each fiber captures light from one galaxy, routes it to a spectrograph, which splits it into component wavelengths. From the spectrum, you read the redshift, how much the expansion of space has stretched the light since it left that galaxy. From the redshift, you get distance and recession velocity. Run this for enough nights, across enough sky, and you build a three-dimensional map of the universe that records not just where galaxies are now, but how they were distributed across billions of years of history. Like reading tree rings, except the tree is the universe, and each ring is a billion years of expansion captured in the spacing of galaxies. The first DESI data release covered 6 million galaxies and quasars, 11 billion years. The team used multiple independent methods, including baryon acoustic oscillations, the fossilized imprint of pressure waves from the early universe, a ruler for measuring cosmic distances that does not depend on any assumptions about dark energy. Every method pointed in the same direction. The direction was not where Lambda-CDM said it should be. What did 6 million galaxies see that the model missed? The parameter describes the relationship between the pressure and energy density of dark energy. Think of it as dark energy's personality. In Lambda-CDM, W equals -1, always, everywhere, at every point in cosmic history. Not measured, defined. When W equals -1, dark energy does not evolve. It does not respond to anything. It simply is, a fixed property of space itself, the same in the early universe as now, as in whatever comes next. DESI measured W across 11 billion years. In the standard model, that measurement should return a flat line at -1. What DESI found was not a flat line. When they fit the data to a model where W varies over time, described by two parameters, the current value W0 and the rate of change WA, combining DESI with the Planck satellite data and Type 1a supernova catalogs, the best fit values came out as W0 equal to -0.45 and WA equal to -1.79. Those numbers mean dark energy was weaker than a cosmological constant in the early universe, has been strengthening over time, has now crossed below -1. The statistical significance of the deviation from lambda, 3.9 sigma. In particle physics, 5 sigma is discovery. At 3.9, DESI was not there yet. But 3.9 sigma does not look like noise. Noise scatters randomly. This signal strengthened with every additional dataset the team added. Every independent check moved it in the same direction, away from -1, not toward it. A universe that has been waiting for a telescope, precise enough to catch it doing something it was not supposed to do. Was this the first time the universe deviated from the model? Or the first time we were precise enough to notice? When the DESI results appeared in April 2024, the cosmology community did not respond with the measured skepticism that usually greets anomalous results. Within days, hundreds of papers appeared. The speed reflected the weight of what was at stake. Dragan Hutera at Michigan said publicly that if the signal held, it would be the most important discovery in cosmology in 25 years. Adam Rees, Nobel Prize 1998, said the combination of DESI and the ongoing Hubble tension suggested something real was happening outside the standard model. 3 months later, Dylan Brute at Boston University published a reanalysis of the largest supernova compilation ever assembled. Over 1,500 Type 1a supernovae spanning from nearby to more than halfway across the observable universe. His best fit values for W0 and WA from the supernova data alone, negative 0.36 and negative 1.84. A separate independent team reanalyzed the Union 3 supernova compilation and found results consistent with Brutes. Combined with DESI, the tension with Lambda-CDM reached 4.2 sigma. 3 independent datasets, 3 independent analysis teams, 3 independent methods, all pointing away from negative 1. At 4 sigma, statistical flukes do not generally reproduce across independent instruments with different systematic errors. Right now, think about what you are doing in this moment. You are sitting somewhere, in a room, on a planet, in a galaxy held together by gravity and dark matter, and all the physics you were taught describes reality. And 4 independent measurements of that reality are saying the dominant force in it, 68% of everything, is not what the model says it is. You cannot see dark energy. You cannot feel it, but it is moving. And it has been moving for 11 billion years. Did you feel certain 30 seconds ago that you understood the ground you were standing on? If W is not negative 1, if dark energy is genuinely evolving, then every calculation cosmologists have made about the history and future of the universe needs to be examined again. Not refined, examined from the beginning. Because W is not one number among many. It controls how dark energy behaves as the universe expands, which controls the expansion rate at every epoch, which controls the distances to every object we observe, which controls the ages we assign to distant galaxies, which controls our entire picture of how structure formed across 13 billion years. Working backward, if dark energy was weaker in the early universe than Lambda-CDM predicts, the expansion rate at early times was different from what the model assumes. The distances we calculated using that assumption are off. The ages we assigned to the earliest galaxies are off. The James Webb Space Telescope has found galaxies at redshifts that look too massive and too evolved for their age under the standard model. Galaxies that seem to have had less time to form than they needed. If dark energy was weaker early on, those galaxies had more time. The anomaly might not be in the galaxies, it might be in the model the ages were calculated from. Working forward, the fate of everything depends entirely on the trajectory of W. Whether the universe ends in heat death, in collapse, in something we have no name for, all of it runs through W. And right now, the trajectory of W is pointing somewhere nobody who built Lambda-CDM expected to look. What do you do with a model when its most certain parameter turns out to be wrong? In 2013, the Planck satellite released its measurement of the Hubble constant, the rate at which the universe is currently expanding. Planck measured this indirectly through the oldest light in existence. It analyzed the cosmic microwave background, light emitted 380,000 years after the Big Bang, reconstructed the initial conditions, ran the standard model forward 13 billion years, and read off the present-day expansion rate. The answer? 67.4 kilometers per second per megaparsec. That same year, Adam Rees and the SH0ES team were finishing a completely independent measurement using a completely different method. They built a distance ladder, Cepheid variable stars in nearby galaxies, whose pulsation period tells you their exact luminosity and therefore their exact distance. From Cepheids, they calibrated Type 1a supernovae. From supernovae, they reached billions of light years out. Their answer? 73 kilometers per second per megaparsec. Rees checked his data. Planck checked their data. Both teams found nothing wrong. The gap was 5.7 kilometers per second per megaparsec. Statistical significance, 5 sigma. Probability of a 5 sigma discrepancy being a fluke, less than 1 in 3.5 million. 2 measurements, 2 methods, 2 answers, and every attempt to find the error has failed. Here is the thing that should unsettle you. Planck gets its answer by assuming Lambda-CDM is correct and running it forward. Reese goes directly to the late universe without assuming anything about dark energy. Every team that uses the early universe approach gets one number. Every team that measures the late universe directly gets a higher number. What happens when the only measurements that agree with the model are the ones that assume the model was correct? Reese and his team have spent every year since 2013 looking for the error in their measurement. They have re-examined every rung of the distance ladder, tested whether the Cepheid calibration is affected by chemical composition, by crowding in dense stellar fields, by dust that reddens the light and biases the brightness. In 2023, they published the first results using the James Webb Space Telescope, which has the angular resolution to separate individual stars in crowded fields that Hubble could not resolve, directly addressing the most serious concern. The value came back unchanged. 73. Independent teams using entirely different distance indicators added their own measurements. The tip of the red giant branch, surface brightness fluctuations of elliptical galaxies, time delays of gravitationally lensed quasars. All of them returned values between 70 and 74, inconsistent with Planck at 2 to 4 sigma. The only measurements that return values near 67 are the ones that derive the Hubble constant indirectly through the standard model. Every measurement that goes to the late universe directly comes back higher. 10 years of checking. The gap has not closed. It has hardened. So here are the two options. Either every independent measurement of the local expansion rate has the same unknown systematic error, the same error that survived James Webb, that survived a decade of searching, that appeared in instruments built on different continents by different teams using different physics, or the standard model, when you run it forward from the early universe to today, does not correctly describe what the universe actually did. Pick the option that seems more likely. Then ask yourself what the answer means for everything else we calculated using that model. There is a version of the story where the Hubble tension and the DESI result are not two separate failures, but one. The idea is called early dark energy. In Lambda-CDM, dark energy is negligible in the early universe. Its energy density is thousands of times smaller than the energy density of matter and radiation when the CMB was emitted. But what if there was an additional component that was significant in the period just before recombination? If this early component boosted the expansion rate slightly at that epoch, Planck would infer a higher Hubble constant from its CMB analysis, closer to what Ries measures directly. Vivian Poulin at the University of Montpellier developed one of the leading early dark energy models in 2018. She worked out the specific signature it would leave in the CMB power spectrum, a precise modification to the acoustic peaks at high multipoles. The Atacama Cosmology Telescope released updated CMB data in 2023. The data showed hints consistent with Poulin's predicted signature, not at discovery significance, but consistent. And the Hubble tension under early dark energy models was reduced by roughly a third compared to standard Lambda-CDM. No other proposed modification has done that. If early dark energy is real, it means dark energy has a history that predates the epoch when it became dominant. Present in the early universe, fading away, now growing again in the way DESI is measuring. 3 separate signals: the Hubble tension, the DESI result, the CMB anomalies from ACT pointing to the same explanation. One force with a history evolving over 13 billion years, leaving fingerprints at multiple epochs that we are only now reading simultaneously. A force with a history has a direction. Where is it going? The history of physics has a pattern. A model accumulates tensions. Each one gets explained away. A systematic error, a statistical fluctuation, an approximation that needs refining. The explanations multiply. The patches accumulate. And then, The weight of the patches exceeds the weight of the model, and the field moves. In 1887, Michelson and Morley used the most precise interferometer of the 19th century to look for the luminiferous ether, the medium through which light was supposed to travel, the way sound travels through air. They found nothing. Zero difference in the speed of light regardless of direction. Physicists spent 15 years patching ether theory. George Fitzgerald proposed that objects physically contract in the direction of motion through the ether. Hendrik Lorentz developed the mathematics of this contraction in precise detail. Both patches were internally consistent. Both accurately accounted for the null result. And both were completely wrong, not in their math, but in their premise. In 1905, Einstein published Special Relativity. No ether. Light needed no medium. Every tension in ether theory dissolved simultaneously, not because the ether was fixed, but because it was gone. Lambda-CDM in 2024 has the Hubble tension, 5 sigma, unresolved after a decade. It has the S8 tension, the mismatch between the predicted and observed clustering of matter. It has the DESI result, 4 sigma deviation in the most fundamental parameter of dark energy. 3 independent tensions, 3 independent datasets, 3 independent methods, 3 separate patches proposed. Early dark energy for the Hubble tension, modified gravity for S8, dynamical dark energy for DESI. What happened the last time physics needed 3 patches at once? If W is not -1, the first question is what dark energy physically is. The cosmological constant is not an explanation, it is a description. To explain dark energy, you need a mechanism. The leading candidate has a name that goes back 2,000 years. Aristotle believed the heavens were made of a 5th element, beyond earth, water, fire, air, that he called the quintessence. Paul Steinhardt at Princeton, Rahul Dev, Robert Caldwell, and Limin Wang revived the word in 1998 and gave it modern meaning. In their model, dark energy is a field, a quantity with a value at every point in space and time. The way temperature has a value at every point in the atmosphere. Not static. The field rolls slowly down an energy landscape, the way a marble rolls down a very shallow slope. As it rolls, the force it exerts on the expansion changes. Dark energy has a trajectory, a history, a direction. The DESI values, W0 of -0.45, WA of -1.79, are consistent with certain quintessence potentials and rule out others. The potential that fits best corresponds to a field that was subdominant in the early universe, became dominant as matter diluted away, and has now rolled past a boundary that the cosmological constant cannot cross. Which means, if quintessence is the answer, dark energy is not a static property of space. It has been rolling for 13 billion years. And here is what nobody says out loud in the summary papers. A field that rolls does not stop rolling just because we measured it. It continues. The question is not just where the field has been. The question is what happens when it gets to where it is going. Do we know where it is going? The second candidate does not add anything to the universe. It changes a rule instead. General relativity, Einstein's theory of gravity, has been tested with extraordinary precision inside the solar system. The precession of Mercury's orbit matches the prediction to 5 decimal places. The bending of light around the sun confirmed during the 1919 eclipse. The timing of signals from binary pulsars tracked for decades and matching the theory to better than 1%. At solar system scales, general relativity is essentially exact. But cosmological scales, hundreds of millions to billions of light years, are a different regime. The equations have never been directly tested there the same way they have been tested in the solar system. The only way we test them cosmologically is by assuming they are correct and checking whether predictions match observations, which is precisely the kind of test that cannot detect a systematic error in the framework itself. You are testing the theory using the theory. Hiroaki Oyasu and Wayne Hu showed in 2008 that modified gravity theories predict a different relationship between cluster mass and abundance than general relativity. The Euclid satellite, collecting data now, was designed to measure exactly those signatures. If Euclid's galaxy cluster statistics match modified gravity predictions better than general relativity, it will be the first evidence that Einstein's equations need revision at cosmic scales. Think about what that actually means. Every distance, every age, every inferred history of how galaxies formed, all of it calculated through equations that turn out to be an approximation, valid only at smaller scales. The map is accurate. The cartography is wrong. How much of what we know about the universe is calculated through equations we have never directly tested at the scales where we use them most? There is a third possibility, and it is the most structurally uncomfortable one. Dark energy and dark matter, together 95% of the universe, may not be independent. They may interact. Energy may flow between them. In Lambda-CDM, dark energy and dark matter coexist without communicating. Dark matter clumps under gravity, providing scaffolding for galaxies. Dark energy accelerates the expansion. They share the same space and exchange nothing. This assumption is not physically motivated. It is a simplification adopted, because the data available when the model was built was not precise enough to detect any coupling. Nobody proved there was no interaction. They just assumed it for convenience. Luca Amendola at Heidelberg developed interacting dark energy models in the early 2000s. In his framework, a coupling term connects the dark energy field to dark matter particles, allowing energy to transfer between them as the universe evolves. The effect modifies how fast dark matter clusters, changes the growth of large-scale structure over time, leaves imprints in galaxy surveys. Crucially, certain interacting models reduce both the Hubble tension and the S8 tension simultaneously. The same coupling that changes the early expansion history also changes the late-time clustering amplitude in a correlated way. Two tensions, one mechanism. The DESI data combined with weak lensing surveys has begun to constrain the coupling strength. The constraints are not yet tight enough to confirm or exclude the interaction. We are measuring the thing. We cannot yet read what it says. But here is the question that Amendola's work raises, and that the field has been circling around for 20 years without landing. What if dark energy and dark matter are not two separate unknowns, but two faces of one unknown? What does it mean that our two largest mysteries might be the same mystery? Three candidates. Quintessence, a field with a history rolling toward an unknown destination. Modified gravity, Einstein's equations revised at scales we have never directly tested. Interacting dark energy, a coupling between the two things we least understand. All three mathematically consistent. All three making predictions that differ from Lambda-CDM in testable ways. All three currently compatible with the data, including DESI. We are not at the point where the data has chosen between them. We are at the point where the data has eliminated the simplest option, the cosmological constant, and left three roads ahead. Each road leads somewhere different. The quintessence road leads to a universe where dark energy has a trajectory and a future shaped by a potential we have not yet mapped. The modified gravity road leads to a universe where the force holding everything together follows slightly different rules than we assumed, which propagates through every number in the field. The interacting road leads to a universe where our two greatest mysteries turn out to be one. Pick the wrong road and you spend a decade designing experiments for the wrong physics. Pick the right one and the next generation of instruments gives you the most important result in cosmology since 1998. Right now, nobody knows which road is right. The road we were on, the cosmological constant, W equals -1, is no longer open. The data closed it at 4 sigma. 3 roads. One signal that something is wrong with the model. And right now, in 11 observatories across 4 continents, instruments are running, data is accumulating, and the answer is somewhere in the numbers already collected. When do we think we will read it? In 2002, Robert Caldwell at Dartmouth published a paper that opened with an apology, not for the math, for what the math implied. He had been working through what the DESI type signal would require if dark energy were to cross below -1, not approach it, but cross it. He called the result phantom energy. He expected it to be a mathematical ghost, something that appeared in equations without corresponding to anything physical. The reason below a -1 is not just unusual, it is that it violates the null energy condition. Every known form of matter and energy satisfies this condition. It states, roughly, that energy density as measured by any observer is non-negative, and that energy cannot flow faster than light. The null energy condition is what keeps cause before effect. It is what prevents closed loops in time from forming spontaneously. It is one of the foundational constraints of classical physics, the bedrock assumption underneath almost every calculation in general relativity. Phantom energy breaks it. In a universe with phantom dark energy, the energy density does not decrease as space expands. It increases. The more space stretches, the more phantom energy there is per unit volume. Space expanding creates more of the thing that makes space expand faster. The process feeds itself, accelerating without limit. The DESI best fit values place W below -1 right now. Not approaching, below. If those values are correct, we are already in a phantom phase. The boundary was crossed, and Caldwell worked out where a phantom phase leads. He published the answer in 2003. The answer has a name. Can you hear the name before I say it? Caldwell, with Mark Kamiankowski and Nevin Weinberg, published the destination of the phantom phase in 2003. The result was a sequence, not a bang, not a sudden event. A sequence, a progressive dissolution, moving from the largest scales of the universe downward to the smallest, at a pace set by how fast the phantom energy density is growing. Here is how the sequence runs. In the early stages, billions of years from now under models consistent with DESI, the phantom energy density becomes comparable to the gravitational binding energy of galaxy clusters. The clusters are the largest gravitationally bound structures in existence, held together by the collective gravity of thousands of galaxies. As phantom energy grows, cluster after cluster loses cohesion. The galaxies that were bound together begin to drift. This happens slowly, across timescales that dwarf the current age of the universe. Then it accelerates. As the density rises further, individual galaxies lose structural coherence. The Milky Way, 10 billion years of spiral structure, loses the gravitational binding of its outer arms. Stars that have orbited the galactic center for billions of years find themselves no longer bound to it. They drift into intergalactic space, one by one, permanently. Then the process reaches stellar scales. Planetary systems disintegrate as phantom energy overcomes the gravitational binding of planets to their stars. Then the planets, then rocks, then molecules. Your body, if anything analogous to a body still exists at this point in cosmic time, is held together by electromagnetic forces between atoms. Phantom energy does not yet overcome electromagnetism. Not yet. What happens when it does? In the final sequence of the Big Rip, Caldwell's name for the endpoint, roughly 30 minutes before the end, the electromagnetic force can no longer hold the atoms in a rocky planet together against the growing phantom pressure. The planet does not explode. Its atoms simply find themselves in a universe where the force that was keeping them bound is no longer the dominant force in their immediate environment. They drift apart, quietly. The same process then reaches molecular scales, then atomic scales. In the last fraction of a second, the strong nuclear force, the force that binds quarks inside protons and neutrons, is overcome. Protons dissolve, neutrons dissolve. The fundamental particles that have been the basic units of matter since 1 microsecond after the Big Bang cease to be bound structures. The quarks drift free, and then nothing. Not darkness, because darkness requires space. Not silence, because silence requires a medium for sound to be absent from. The universe reaches maximum entropy not through slow cooling over trillions of years, but through dissolution. Caldwell calculated that if W equals negative 1.5 and stays there, the Big Rip occurs roughly 22 billion years from now. For values closer to -1, like the DESI best fit, the timescale extends, possibly to hundreds of billions of years. We do not know if the Big Rip is our future. The DESI data is consistent with it. That is not the same as predicting it, but sit with the shape of it. The universe spent 13 billion years building structure: atoms, stars, galaxies, life, thought, questions. And it ends not in a decisive moment, but in a quiet unraveling, starting at the largest scales and working inward until there is nothing left that is bound to anything else. The universe does not end. It just stops holding together. Is that more terrifying or less than an explosion? There is something in the DESI result that received almost no coverage when the paper was published. The best fit values, W0 of -0.45, WA of -1.79, do not just place dark energy below the phantom line now. They imply that dark energy crossed the phantom line recently, in cosmological terms, within the last few billion years. Before the crossing, W was above -1. After it, below. Dark energy changed character. And a field that crosses this boundary is not just unusual. In most theoretical frameworks, it is physically impossible for a single field to do this. A single scalar field, like Quintessence, cannot cross below -1. The equation of state of a single scalar field is bounded from below by -1. To cross it with a single field requires violating the null energy condition at the field theory level, which produces ghost degrees of freedom, modes in the theory that carry negative kinetic energy, making the theory unstable in ways that cascade without limit. You get a theory where energy is not conserved in any useful sense. To cross the phantom divide smoothly requires at least two fields, a quintessence field and a phantom field, acting together. Models built on this are called quintom models, developed by Feng, Wang, and Zhang in 2005, specifically to allow the trajectory DESI is now measuring. The fact that the data prefers a trajectory crossing W equals -1 is a direct measurement pointing beyond any single field model. Whatever dark energy is, it is more complex than a single evolving field. Something in the dark sector, in the 80% of reality we cannot directly see or touch, is more complicated than we allowed for. How much more complicated? The number 10 to the power of 120 is not just large. It describes how improbable your existence is. Take the observed value of the cosmological constant and ask, over what range of values would the universe still contain galaxies, stars, planets, any form of complexity? The range, worked out by Weinberg in 1987, is roughly a few times 10 to the power of -122 in Planck units. The total range the cosmological constant could in principle take spans 122 orders of magnitude. The slice compatible with a universe containing observers is 1 part in 10 to the power of 120. Here is an image for that. The surface area of the observable universe is roughly 10 to the power of 54 square meters. Imagine a surface 10 to the power of 120 times larger. Pick a random point on it. The probability of landing within the tiny patch that allows galaxies to form is the same as the probability that the cosmological constant landed where it did by chance. There is no word in any language for a probability that's small. Small does not begin to cover it. And right now, in your body, in this room, in this moment, you are the consequence of that landing. Every atom of carbon in you, every iron nucleus in your blood, every calcium crystal in your bones exists because the number landed in that unimaginably narrow window. The fact that you are here is not a given. It is the evidence of an improbable precision that nobody can explain. The universe did not have to produce you. By any reasonable accounting of the odds, it should not have. Do you feel lucky? Or does lucky not begin to cover it either? The Anthropic principle says, we observe the cosmological constant to have the value it has because if it had any significantly different value, we would not be here to observe anything. Logically true, deeply unsatisfying. David Gross, Nobel Prize 2004, Quantum Chromodynamics, has said publicly that the Anthropic principle is a dangerous idea that threatens to replace physical explanation with selection effects, when any observation can be explained by noting that observers only observe universes compatible with their existence. You have a principle that explains everything. A principle that explains everything explains nothing. It is the most useful, useless idea in physics. But here is what makes the cosmological constant problem different. The window of values compatible with structure formation is not just narrow. It is narrow in a specific, calculable way. And the distribution of values that different theories predict is not uniform. String theory predicts a specific distribution over a vast landscape of possible vacuum states. If that landscape is populated, if different regions of a larger reality realize different vacuum states, then the probability that our vacuum lands in the anthropically allowed window is not infinitesimally small. It is of order 1. Because we are, by definition, in a region where it must. The Anthropic principle converts from philosophical retreat into a statistical prediction. The universe is not fine-tuned against the odds. It is one of the rare instances selected for by the structure of the landscape itself. And the DESI measurement of a changing W is now constraining which regions of the landscape are compatible with our expansion history, eliminating classes of vacua, narrowing the theoretical space. The landscape is vast. Measurement is starting to carve it. Is that comforting, or does it make the size of what we do not know feel larger? Leonard Susskind estimated in 2003 that the string landscape contains roughly 10 to the power of 500 distinct vacuum states. Each corresponds to a different way of compactifying the extra dimensions string theory requires. Each compactification produces a different cosmological constant, different particle masses, different coupling constants, a different physics. In most of these universes, the cosmological constant is catastrophically large, and no structure forms. In a tiny fraction, it lands near 0. In an even tinier fraction, it lands in the window that allows planets, chemistry, observers. Raphael Bousso at Berkeley and Susskind developed the cosmological implications across a series of papers in the early 2000s, building on eternal inflation, the idea that the universe is an endlessly producing foam of bubble universes, each nucleating from quantum fluctuations of an inflating background, and each realizing one of the landscape vacua. In this picture, the question is not why our vacuum has the cosmological constant it has. Every value is realized somewhere. The question is why we are in this one. The answer is the one Weinberg gave in 1987, now embedded in a physical framework. We are here because here is one of the places where here is possible. Whether this is correct is genuinely unknown. It is consistent with DESI. It is not yet falsifiable in the sense that a single experiment could definitively rule it out. But it is the only framework that makes the cosmological constant not a miracle, but a consequence. 10 to the power of 500 universes. Most of them empty. Most of them hostile to any form of structure. And here you are, in one of the rare ones, reading about the rest. Does the existence of the others make this one feel more meaningful or less? In 2023, the European Space Agency launched the Euclid satellite to the second Lagrange point, 1.5 million kilometers from Earth. Its primary mission, measure the shapes of 2 billion galaxies across a third of the sky. The minute distortions in those shapes, caused by gravitational lensing as light bends around intervening dark matter, build a three-dimensional map of the universe's large-scale structure. From this map, Euclid measures both expansion history and the growth rate of structure simultaneously, separating dark energy models that produce the same expansion history but different clustering signatures. The two properties together create a fingerprint. Different theories leave different fingerprints. The Nancy Grace Roman Space Telescope, launching in 2027, conducts a survey of half the sky at Hubble-level resolution. Its supernova program will detect tens of thousands of Type 1a supernovae, more than 10 times the current total, measuring the expansion history with a statistical precision that resolves degeneracies between dark energy models that current data cannot break. The Simons Observatory in the Atacama Desert, completing construction now, measures CMB polarization at 10 times Planck's sensitivity. Among its targets, the specific early dark energy signatures predicted by Poulin's models, and the lensing of CMB photons by large-scale dark matter structure, independently constraining the clustering amplitude. Within 5 to 10 years, every major tension in Lambda-CDM has a definitive answer from independent high-precision instruments. The DESI signal will either sharpen to discovery significance or wash out. The Hubble tension will either survive or be traced to a systematic error. The answer exists somewhere in the data being collected right now. What happens to our understanding of the universe if all three tensions confirm simultaneously? In 2012, ATLAS and CMS at the Large Hadron Collider announced the discovery of the Higgs boson. Mass: 125.09 gigaelectron volts. Front page news everywhere. Completion of the Standard Model. What was not front page news was what that specific mass meant for the stability of the ground state of the universe. The Higgs field permeates all of space. Every massive particle acquires its mass through interaction with it. The field sits in an energy minimum, a valley, and the depth of that valley determines whether the vacuum we inhabit is the true lowest energy state or a metastable one, a local dip on a slope, not the bottom of the mountain. In 2012, Shaposhnikov and Veterik at CERN calculated the Higgs self-coupling from the electroweak scale up to the Planck scale using the measured Higgs and top quark masses. They found the self-coupling passes through zero at roughly 10 to the 11th gigaelectron volts and becomes negative above it. A negative self-coupling means the Higgs potential develops a second, deeper minimum at very high field values. The minimum we are in is not the bottom. There is a lower valley. We are sitting on a slope, held in the local dip by a barrier. Think of it this way. Every valley in a landscape is stable until something gives the marble enough energy to roll over the rim and fall into a deeper valley. The marble has been sitting in our valley for 13.8 billion years. Nothing has rolled it over the rim yet. That is not the same as saying the rim is not there. What is on the other side of the rim? If the Higgs field tunnels into the true vacuum, the process does not happen everywhere at once. It happens at a single point, a quantum fluctuation of the right size in the right configuration, and produces a bubble of true vacuum surrounded by the metastable vacuum we inhabit. Inside the bubble, the laws of physics are different. Particle masses change. The fine structure constant changes. The binding energies that hold atomic nuclei together take different values. The chemistry underlying every biological process requires specific values of these constants. In the true vacuum, those values are different. Atoms as we know them cannot exist inside the bubble. Sidney Coleman worked out the mathematics at Harvard in 1977. The bubble expands at the speed of light. There is no physical mechanism by which it can expand more slowly. The energy released propagates outward at the maximum speed physics allows. This means the information that the bubble exists and the bubble itself travel at the same speed. No signal can outrun it. No warning can precede it. Right now, in a galaxy a billion light years away, a bubble of true vacuum could have nucleated a billion years ago. It is traveling toward you at the speed of light. The light from that galaxy is reaching your eyes in this moment, showing you a perfectly normal spiral structure. Stars forming, planets orbiting, everything exactly as expected. The bubble is also reaching you in this moment. Both arrive simultaneously. One shows you what the universe looked like a billion years ago. The other ends what the universe is right now. Between seeing and not being, there is no interval. You are reading this sentence, and then you are not. And the not is not experienced by anything. Are you certain that is not happening right now? The Coleman-de-Lucia calculation gives a nucleation rate per unit volume per unit time. For the electroweak vacuum with the measured Higgs mass of 125.09 giga-electron-volts and top quark mass of 172.76 giga-electron-volts. This rate is extraordinarily small, roughly 10 to the power of minus 394 events per cubic meter per second. The expected time before a tunneling event occurs anywhere in the observable universe is many orders of magnitude longer than the current age of the universe. On these numbers, vacuum decay is not a near-term concern on any human timescale. But the calculation has a limitation rarely discussed outside technical papers. It assumes we are in the vacuum ground state everywhere, with no high-energy excitations. In the early universe, at temperatures far above the electroweak scale, roughly 100 giga-electron-volts, or about 10 to the 15th Kelvin, the Higgs field was subject to thermal fluctuations vastly larger than anything occurring today. At those temperatures, the field was not sitting quietly in the local minimum. It was being kicked continuously by thermal energy comparable to the height of the barrier separating our vacuum from the true one. Any physics beyond the standard model operating at those energies, and there must be such physics, because the standard model cannot account for dark matter, the matter-antimatter asymmetry, or the observed neutrino masses, could have produced field configurations large enough to trigger the transition. The universe is still here. That means no such event occurred in the first fraction of a second after the Big Bang. That is the evidence that the vacuum survived the early universe. It is not a calculation of what happens next. And here is the connection to everything we have been tracking. If a dark energy is a dynamical scalar field, if quintessence is real, that field evolves through the same space-time as the Higgs field, coupled to it through gravity at minimum, and possibly through direct non-minimal coupling terms in the Lagrangian. A quintessence field rolling down its potential releases energy into the gravitational sector. The coupling strength is parameterized by a dimensionless number, x sub I, typically assumed to be small or zero in most quintessence models. But assumed to be zero is not measured to be zero. No experiment has constrained C to better than order unity at cosmological scales. The stability of the vacuum and the evolution of dark energy are not independent problems sitting in separate rooms. They share the same space-time. They are coupled through the same gravitational sector. We are analyzing them separately because it is mathematically convenient. Whether the universe cares about our convenience is a different question. Right now, in your body, your atoms, your nuclei, your quarks sit in the metastable vacuum. The quintessence field, if it is real, is rolling. The two processes share the same space-time. We are analyzing them separately. Should we be? There is a quantity called the equation of state, and we have been discussing it as W. But there is a more fundamental way to think about what W measures. W measures how the universe wants to end. Not metaphorically, literally. The three possible fates, heat death, big crunch, big rip, are distinguished entirely by the value and trajectory of W, once you are in the future where dark energy dominates over everything else. And DESI has measured W changing, which means the universe's preferred ending has been shifting. Or rather, we are only now precise enough to see what it was doing all along. The mathematics behind this is direct. The Friedmann equations, derived from general relativity in 1922 by Alexander Friedmann, relate the expansion rate of the universe to its total energy content. Written out, the first Friedmann equation states that the Hubble parameter squared equals 8 pi g divided by 3 times the total energy density. The second Friedmann equation, the acceleration equation, states that the second derivative of the scale factor divided by the scale factor equals minus 4 pi g over 3 times the quantity rho plus 3p, where rho is the energy density and p is the pressure. For dark energy, P equals W times rho. When W equals -1, the term rho plus 3p equals rho minus 3, rho equals -2 rho, negative. A negative source term in the acceleration equation means the acceleration is positive. The universe expands faster over time. When W crosses below -1, the pressure term becomes even more negative, the acceleration grows without bound, and the energy density of dark energy increases rather than decreasing as space expands. This is the phantom regime. The scale factor in a phantom-dominated universe does not grow smoothly toward infinity. It diverges at a finite time. That finite time is the Big Rip. If the DESI trajectory continues, below -1, continuing to decrease, the Big Rip is the destination. For W of -1.5 and constant, roughly 22 billion years. For W of -1.2, roughly 100 billion. For values very close to -1, timescales extending to hundreds of billions of years, possibly indefinitely if W by asymptotes upward before reaching the critical threshold. The DESI data gives us the current value and the rate of change over the past 11 billion years. Extrapolating forward requires assuming the rate of change stays constant, an assumption with no physical justification. The field could continue, it could stabilize, it could reverse. What the next surveys, Euclid, Roman, the full DESI dataset, will tell us is not just what dark energy is. They will tell us with unprecedented clarity what the universe intends to do with itself. That answer is being measured right now. It exists in data on servers in Arizona, in Chile, in orbit above the Earth. What kind of universe do you want to be living in when you read that answer? Here is the position we are in right now in 2024. The discovery that the universe is accelerating was made in 1998. The model built around it, Lambda-CDM, survived every test for 25 years at the precision those tests were run. The instruments now challenging the model are producing data at precision levels that did not exist when the model was built. The model was assembled at a certain resolution. We are now looking at higher resolution. At higher resolution, the model has cracks in it that the lower resolution was too coarse to see. To understand how precise DESI actually is, consider the baryon acoustic oscillation measurement. In the early universe, before recombination, the plasma of baryons and photons supported acoustic pressure waves. Sound waves propagating through the hot, dense medium at roughly 57% of the speed of light. When the universe cooled enough for atoms to form at 380,000 years, the waves froze in place. The characteristic scale of those frozen waves, the sound horizon, is 147.09 megaparsecs, calculated from the physics of the early universe with extraordinary precision. This scale is imprinted as a preferred separation in the distribution of galaxies across the sky. Measuring this preferred separation at different redshifts gives you the angular diameter distance and the Hubble parameter at each epoch. DESI measured the BAO scale at 7 distinct redshift bins, from z equals 0.1 to z equals 2.1, spanning the last 11 billion years of expansion history. The precision on the BAO scale in the lowest redshift bin, 0.5%. At that level of precision, a deviation of W from -1 by even 0.1 produces a measurable shift in the inferred distances. This is what the scientific process looks like when it is working. Not failure, not crisis. A precision threshold crossed. The 1998 instruments justified Lambda-CDM. The 2024 instruments exceed that justification. The model that was adequate at one level of measurement is insufficient at the next. Not wrong the way a factual error is wrong, but insufficient the way Newtonian mechanics is insufficient when you need to account for the speed of a GPS satellite. The predictions are accurate within the domain where the approximation holds. Outside that domain, something more complete is needed. What nobody knows yet is how much more complete. Whether the successor to Lambda-CDM will be a modest revision, a quintessence field, gravity equations adjusted at large scales, or something that requires the kind of conceptual overhaul that relativity required when it replaced the ether. The data will decide. The data is being collected. We are living through the narrow interval between the question being precise enough to answer and the answer arriving. Does that feel like luck or like vertigo? Here is what is established and what is not, stated plainly. The expansion of the universe is accelerating, confirmed at overwhelming significance by multiple independent methods. Something is causing this acceleration, certain. The standard description of that something as a fixed cosmological constant with W equal to -1 is in tension with the data at 4 sigma, current state of the evidence. What that something physically is, its nature, its origin, its trajectory, not established. Unknown. 68% of everything. Unknown. The specific numbers from the combined DESI plus Planck plus supernova dataset. W0 equals -0.827 plus or minus 0.060. WA equals -0.75 plus or minus 0.29. These are the marginalized constraints on the CPL parameterization, the Chevalier-Pulaski-Linder framework, where the equation of state is written as W of it equals W0 plus WA times 1 minus A, with A being the cosmic scale factor normalized to 1 today. In this parameterization, W0 is the present-day value, and WA characterizes the rate of evolution, how fast W was different in the past. The combination W0 plus WA gives the equation of state at very early times, in the limit as A approaches 0. For the DESI central values, W0 plus WA equals -1.577. This means dark energy in the early universe was significantly more negative than the cosmological constant, more phantom-like in the past, and has been evolving toward less negative values over time. The trajectory, in other words, is moving away from the Big Rip scenario, not toward it, unless it reverses, which the current data cannot tell us. This is not comfortable. And what makes 2024 different from every previous year since 1998 is not that the problem got larger. It was always this large. What changed is that the data became precise enough to tell us the placeholder description was wrong. That is progress. It does not feel like progress. Progress toward a harder problem feels like moving backward. But the harder problem is the real problem. We do not know whether dark energy is a field, a modification of gravity, an interaction between unknown components, or something that has not yet appeared in any theoretical framework. The history of physics suggests the last option has at least as much probability as the others. Whatever dark energy turns out to be, the framework that explains it will probably require abandoning a concept that currently feels essential. What concept are you most certain of right now? In 2029, DESI completes its full 5-year survey, 40 million galaxies and quasars. The precision on W0 and WA improves by a factor of 3 to 4 over the 2024 first release. If the signal is real, it crosses 5 sigma, discovery. If it is a statistical fluctuation, it washes out toward -1. By 2030, the ambiguity about whether the equation of state is changing ends. To understand what that precision improvement actually means, consider the Fisher matrix forecast for the full DESI survey. The figure of merit, a standard measure of dark energy constraining power defined as the inverse of the area of the W0-WA confidence ellipse, increases from roughly 27 in the year 1 release to approximately 100 in the 5-year dataset. A figure of merit of 100 means the joint uncertainty on W0 and WA shrinks to an ellipse roughly 4 times smaller in area than the current constraints. At that level, the deviation of W from -1 that DESI is currently measuring at 3.9 sigma would either harden to 7 or 8 sigma, well beyond any reasonable doubt, or disappear entirely into the noise. There is no middle outcome. The 5-year data is definitive. Alongside DESI's 5-year release, Euclid publishes its first major cosmological results by 2027. Galaxy weak lensing and galaxy clustering combined, constraining the growth rate of structure independently of the expansion history. The key number Euclid targets is the growth index gamma, which parameterizes how fast matter clusters under gravity. In general relativity, gamma equals approximately 0.55. In most modified gravity theories, gamma deviates from this by 5 to 20%. Euclid measures gamma to roughly 2% precision. If gamma comes back at 0.55, general relativity survives at cosmological scales. If it comes back at 0.48, the prediction of the most studied FR gravity models, the implications propagate through every calculation in the field. Are you paying attention to what is coming in 5 years? The question that dark energy points toward, underneath all the measurements, all the tensions, all the model comparisons, is a question physics has been circling for a century without landing. Not how much vacuum energy, why any? Why is the ground state of quantum field theory not zero energy? Why does empty space weigh something? The technical statement of the problem goes deeper than the number 10 to the power of 120. In quantum field theory, every field contributes to the vacuum energy through zero-point fluctuations. For a scalar field of mass m, the contribution to the vacuum energy density is of order m to the 4th power, divided by 16 pi squared, in natural units. Summing over all known fields, the quarks, the leptons, the gauge bosons, the Higgs, and integrating up to the Planck scale, where quantum gravity presumably cuts off the integral, you get the number Weinberg calculated. The vacuum energy density is of order 1 in Planck units, meaning 1 unit of energy per cubic Planck length, where the Planck length is 10 to the minus 35 meters. The observed dark energy density is 10 to the minus 123 in those same units. The ratio is 10 to the minus 123 over 1. The inverse of the number we have been discussing throughout this video. 0.1, 2, 3, all the way to the 123rd decimal place. All zeros. And then the actual number. That is the fine-tuning. Not a rough estimate. A precise statement about decimal places. Every answer physics has produced is a description, not an explanation. The cosmological constant describes the vacuum energy without explaining it. Quintessence describes a rolling field without explaining why the potential has the shape it has. The string landscape describes a vast ensemble of possible vacuum states without explaining why any of them are populated. Each framework pushes the question back one level and leaves the deepest level untouched. Gottfried Wilhelm Leibniz asked in 1714, "Why is there something rather than nothing?" Dark energy is where this question is most visible, most acute, most practically consequential. It is 68% of everything that physics cannot yet explain. And the fact that it is accelerating the universe, possibly evolving, possibly headed somewhere that ends in the dissolution of all structure, that is not an abstraction. That is the condition you are living in, right now. What does it feel like to know that the force driving the universe apart is something physics cannot explain, and that it is doing it right now, around you, in the space between your atoms? You are made of the 5%. Every atom in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, is part of the tiny fraction of the universe that consists of ordinary matter. The matter described by the Standard Model, the matter we understand. The dark matter flowing through this room right now passes through you without interaction. The numbers. The local dark matter density near Earth is approximately 0.3 giga-electron-volts per cubic centimeter, roughly half a proton mass worth of dark matter in every cubic centimeter of space around you right now. Through your body, which occupies roughly 70 liters of volume, approximately 35 gigaelectronvolts of dark matter is passing at any given moment. The equivalent mass of 35 protons, invisibly flowing through your tissues at hundreds of kilometers per second, interacting with none of the atoms that make up your cells. The cross-section for dark matter interacting with ordinary matter is constrained by direct detection experiments. Lux, Zeppelin in South Dakota, Xenon T in Italy, to be smaller than 10 to the minus 47 square centimeters per nucleon for the most common dark matter mass range. That is 1/10,000,000th of the cross-section of a proton. The dark matter passes through you and feels nothing. You feel nothing. The most sensitive experiments ever built have spent decades trying to catch a single dark matter particle interacting with a single nucleus. As of 2024, they have caught nothing. The dark energy filling the space between your atoms is pressing outward on the universe at a pressure of negative 6 times 10 to the minus 10 joules per cubic meter. Negative because dark energy has negative pressure, the defining property that makes it accelerate the expansion. In every cubic meter of space inside your body, the dark energy contribution is pushing the fabric of space-time outward. The force is absurdly small at these scales, completely unmeasurable by any instrument that exists or is conceivable, but it is there, in the space between your atoms, doing what it does, indifferent to everything you are. The 5% is the part of the universe that organized itself into something that can ask questions about the other 95%. The dark matter does not wonder what it is. The dark energy does not contemplate its own equation of state. Does it seem strange to you that the part of the universe that cannot account for itself is also the only part doing the accounting? When the DESI collaboration published their first data release in April 2024, the paper ran to over 100 pages. The appendices alone were longer than most journal articles. The collaboration involved over 900 scientists from 70 institutions across 13 countries. The data reduction pipeline processed spectra from 6 million objects, each spectrum containing thousands of individual wavelength measurements. Each wavelength measurement calibrated against a grid of known stellar spectra to correct for the instrument's response function. The systematic error budget alone required a separate paper of 40 pages. A careful accounting of every known source of bias, from fiber positioning errors of less than 5 micrometers to variations in the atmospheric dispersion across the 6-hour observing windows. And buried at the end of the conclusions, after all the statistical analysis, all the systematic checks, all the model comparisons, was a sentence that captured the exact position physics now occupies. The team wrote that their results were consistent with a dynamical dark energy model, and that future observations would determine whether the deviation from Lambda-CDM represented a genuine departure from the standard cosmology. The statistical tension with the cosmological constant in the full DESI plus external data combination breaks down as follows. In the W0 to WA parameter space, the point W0 equals -1, WAR equals 0, the Lambda-CDM prediction sits at 3.9 sigma from the best fit point in the combined analysis. The probability that a chi-squared statistic exceeds this value by chance if Lambda-CDM were true, roughly 1 in 10,000. Not impossible, not a discovery, but 10,000 runs of this measurement in a universe where Lambda-CDM is correct would produce a fluctuation this large only once. Marek Ishak at UT Dallas, one of the senior authors, said that the universe keeps declining to be simple. That sentence was not in any press release, but it is the most accurate description of what the data has been saying for 25 years. What happens if it keeps declining? There is a version of this story that ends in despair. 68% of everything is unknown. The ground state of the universe is metastable. The equation of state of dark energy may be driving toward a future where all structure dissolves. The questions at the bottom of the problem may require a conceptual framework that does not yet exist. That is one way to carry all of this. Here is another. You are sitting somewhere, right now, doing something that took 13.8 billion years to become possible. The universe spent its first 380,000 years too hot and dense for atoms to form. A plasma of free particles, opaque and featureless, with a temperature of roughly 3000 Kelvin at recombination. Then it spent several hundred million years in darkness. No stars, no light beyond the cooling background radiation. The cosmic dark ages. The first stars ignited roughly 200 million years in, burning hot and fast, living tens of millions of years instead of billions, seeding the interstellar medium with carbon, oxygen, nitrogen. The second generation of stars formed from that enriched gas, and the third, and your sun, formed 4.6 billion years ago in an unremarkable spiral arm of an unremarkable galaxy that had already been forming stars for 9 billion years before it arrived. Your planet formed from the leftover of that cloud in roughly 100 million years. Life appeared roughly 3.8 billion years ago. The first cells with nuclei, eukaryotes, appeared 2.1 billion years ago. Multicellular life, 600 million years ago. Vertebrates 525 million years ago. Your genus, Homo, 2.8 million years ago. Your species, 300,000 years ago. You, some decades back. At every step in that chain, the cosmological constant had to sit inside its narrow window. The dark matter density had to be close enough to the observed value for galaxies to form, with the right structure for second-generation stars to accumulate. The Higgs mass had to be close enough to 125 giga-electron volts for protons to be stable and chemistry to work. All of it, simultaneously, for 13.8 billion years, without a single parameter drifting outside its window. And in those decades since you appeared, you worked out that the universe is accelerating, that dark energy is 68% of everything, that its equation of state is changing, that the future of all structure depends on a trajectory you are in the process of measuring. The universe produced something that can measure the universe. Does it change anything, knowing that? In 1998, 2 teams pointed telescopes at exploding stars and found the universe was accelerating. 3 people shared the Nobel Prize. The discovery opened a question that has not been answered in 25 years. In 2024, a telescope in Arizona mapped 6 million galaxies across 11 billion years and found that the force driving the acceleration was not what the 1998 model assumed. The question got harder and closer. We know more specifically what we are looking for. And further, because what we are looking for is more complex than what we thought. This is the pattern. Every time the universe is measured at higher resolution, it contains more structure than the previous resolution could see. The progression is quantifiable. In 2000, the best constraints on W came from the original supernova surveys. Sigma of W roughly plus or minus 0.3. By 2010, combined CMB and supernova data brought this to plus or minus 0.08. By 2018, the Planck final release combined with baryon acoustic oscillations from BOSS, the Baryon Oscillation Spectroscopic Survey, predecessor to DESI, brought the constraint on W to plus or minus 0.04, assuming W was constant. DESI's Year 1 release constrains the evolving equation of state, 2 parameters simultaneously, to sigma of W0 equals 0.060, and sigma of WA equals 0.29. The 5-year survey will reduce these by a factor of 3. Each factor of 3 improvement in precision has historically revealed new structure that the previous precision missed. The improvement from BOSS to DESI Year 1 revealed the 3.9 sigma deviation. What will the improvement from DESI Year 1 to DESI Year 5 reveal? The next model will describe dark energy not as a constant, but as something that evolves. It will account for the Hubble tension and the S8 tension and the DESI result simultaneously. Because a model that requires 3 separate patches for 3 separate problems is not the right model. And when it arrives, it will be measured against Euclid, Roman, Simons, the full DESI survey, and it will either survive that measurement or not. The universe does not owe us an explanation we can understand. It does not guarantee that the answer will be accessible to human mathematics or human intuition. What it has done, consistently, across a century of cosmology, is respond to better measurement with richer structure. Every time we looked more carefully, there was more there. Right now, in 2024, the best map of the universe ever made shows a 4 sigma deviation from the standard model. 3 next-generation instruments are in operation or preparation. The answer to what dark energy physically is, the answer to 68% of everything, is somewhere in the data being collected at this moment. You will live to read it. What kind of answer do you think it is going to be?